Math 2414, arc length, video 1, arc length formula. So far in this series of videos on applications of integration, we found the area between two curves, which was an immediate consequence of the fact that a definite integral will tell you the area under a curve if your curve is above the x-axis. We found the volumes of some solids, usually by revolving the lamina around an axis, although it's not critical that you obtain the solid that way. And we found those volumes using one of two techniques. We would take a slice perpendicular to the axis of rotation, take a look at that surface, come up with a formula for the area of that surface based on the x-coordinate where we cut it, or y-coordinate as you will, and then integrated that over the correct interval. But we also found volumes using what was called the shell method, where we took a cut parallel to the axis of rotation and then set up an integral to find the volume of the resulting solid. In this series of videos, we're going to use integration to help us calculate an arc length, the length of a graph. So here's the setup. Suppose y equals f of x is continuous on some closed interval from a to b. Translation. Between A and B, this graph doesn't have any breaks, doesn't have any asymptotes, doesn't have any holes. If we want to find the arc length, we're going to go back to a technique kind of similar to what we did at the beginning of definite integrals. Towards the end of Calculus 1, when you had some graph that was curvy, the genesis of all this was finding the area underneath this. Well, we don't have a nice geometry formula for finding the area underneath something that's curvy like this. So what we did is we partitioned the x-axis, we shot up some rectangles above each of those partitions. Within each partition on the x-axis, we would pick an x value to send through to determine the height of the rectangle. We would set up an expression representing the sum of the areas of these rectangles, the base times the height, and then we took a limit. And the limit was the limit as the widths of the rectangles all approach 0, then this rectangular approximation got closer and closer to the actual value of the area, and at the end it turned into a definite integral. But the game plan there was, let's turn something we don't know how to do into something that is approximately, into something that we do know how to do, that it gives us a good approximation, which in this case was cut into rectangles because those are easy to find areas of. Set up an expression and then take the correct limit. We're going to do the same thing here. So how are we going to do that over here? Well, first we have to think, is there some similar idea that we already know how to do in terms of finding the length of something? And the answer is yes, if you think in terms of distances. If we did the same thing here by cutting this into some intervals, and then above this, locating all the points on the graph above these partition points, if you will, then we could think of this curve as a sequence of roughly straight line segments, so approximately straight line segments. For example, from here to here is not exactly a straight line segment, but it's pretty close. So our strategy is going to be to come up with an expression for the sum of the lengths of these line segments and then take a limit so that the answer we get as a result of that limit should give us the actual length of this curve. Okay, so that's neat, but how are we going to do that? Well, in order to show you, I'm going to have to zoom in on one of these. So I'm going to pick this curvy segment here, and I'm going to blow it up a little bit. Let's say that's the actual curve, y equals f of x. But if we connect the endpoints of that piece, we get that line segment. That red line segment is a good approximation for this arc length if we were to zoom in on this piece right here. So let's go with that. All right, so how can we do this? Well, as far as this partition down here, when we did this, or when you did this back in Calculus 1, we would call each of these widths a delta x, and all of them were the same width. Although if you get to real analysis, you'll learn that they don't all have to be the same width. That's just for convenience at this level of calculus. So if we call the length of this partition piece down here delta x, where would that be in this picture over here? If we moved it up here, it would be like the horizontal displacement from here to here. So this would be delta x, the width of that partition piece. But what about this value? Well, we can't just call it delta y because it's a change in y values. We could be more specific, and we could call it f of x plus delta x minus f of x, meaning this height minus that height. But let's not worry about getting too specific with the details right now. If you are in my class and you want to see all the details, then I recommend you read page 387 in our textbook. Let's see. But anyway, let's call this vertical displacement delta y. And what we're looking for is the length of this line segment here. Let's call that length, I don't know, we could call it a variety of things. Let's see if this author calls it anything in particular. I don't like what he calls it. So let's just call this length, well, let's call it d for distance. And technically speaking, these should have some I subscripts, because when you do a partition on the x-axis, you really partition it by saying x0 is whatever this a is, and then x1, and then x2, and then x3, all the way down to whatever the last one is, you call it xn. So really, when we talk about a delta x and a delta y and a d, we should make reference to the partition that it comes from. Now this is from the second one, but it was just generically selected. So we'll say it's from the ith one. So I'm going to subscript each of these with an I, including the d for distance, meaning that we're doing this picture on the ith subinterval, whichever one it is. All right, so what is it we're trying to do? Oh yeah, we're trying to come up with an expression to represent this distance along this red segment here. But it shouldn't surprise you that I just set up a right triangle, and as a consequence, we can do the Pythagorean Theorem. So, the square of that hypotenuse, the square of di, is going to equal the square of the delta xi plus the square of the delta yi. So let's put all those in there. Delta xi, delta yi. And so to figure out a value for d, I can just square root both sides. And we'll switch to one color now. Therefore, the length of that segment, in terms of delta x and delta y, is the square root of the sum of the squares of the deltas. Okay, so we have a linear approximation for the arc length above this subinterval on the x-axis. So that means that we can take the sum of those. Therefore, the arc length I can spell the arc length, L-E-N-G, that's correct. And the variable for which is, you'll never see this one coming, the variable for arc length is a lowercase s. From now on until forever, lowercase s means arc length. But that arc length is going to be approximately the sum of those distances. So the sum of the square root of the sum of the squares of the delta x and delta y. All right, we're off to a pretty good start, but to get the actual arc length, we have to let the delta x approach 0. In other words, we got to collapse all of these subintervals down to a single point of width 0, so that each of these line segments eventually becomes a single point, so to speak, and then we get the actual arc length. But before we do that, I'm going to massage this a little bit. And the reason I'm doing that is when we originally did Riemann sums, or when you did them in your Calculus 1 class, there was a delta x at the end that became a dx when we took the limit. And currently, I have no delta x on the end. In the Riemann sum, there was a delta x there because we found the area of a rectangle and its base was delta x long. So how can we sneak a delta x on the end here without changing the value of this expression? Well, here comes some algebraic shenanigans, some hand-waving, if you will. There's a real easy way to throw in any factor you want in an expression. I'll throw it in over the end here, because this will become the dx when we take a limit. The way to throw it in there is to multiply by its reciprocal to balance it out. And kind of like when you're balancing out a u substitution whose du is missing a constant. But if we throw a delta x at the end and multiply it by its reciprocal in front of it, now we've got that extra 1 over delta x. And what am I going to do with that? Well, I'd like to multiply this into the square root, but the problem is you can't multiply something outside of the square root with something inside of the square root. So I want to trick out this 1 over the square, 1 over delta xi so that it lives under a square root. And the easiest way to do that is to put a square root over it and square it. I also squared the 1, but it's still 1, so you can't tell the difference. So by rewriting 1 over delta x as the square root of 1 over delta x squared, now I can put the two square roots together and multiply their insides. But think about what will happen when I do that. When I move this 1 over delta x squared into the other square root and distribute it, this 1 over delta x squared times this delta x squared will multiply to give me 1. But this 1 over delta x squared, when multiplied times this delta y squared, I can combine those into a single fraction and have delta y over delta x collectively squared. So it's a little bit of trickery, but I'll be honest with you, and in levels of math this and beyond, trickery like that isn't considered out of the normal. I got something multiplied outside of a square root, I would like to put it inside the square root. All right, whatever you have on the outside, square it, put it under its own square root, and now you can put it on the inside. So how does this help us? Well, this is approximately our arc length. But to get the exact value of the arc length, we have to take the limit as delta x is equal to 0. So what does that give us? I think I'm done with this picture. The actual arc length is the limit as delta x approaches 0 of that expression, the sum of the square root of 1 plus the square of delta y over delta x times delta I. This is a Riemann sum. A Riemann sum is the limit as delta x approaches 0 of the sum of a function times delta x, which gives us a definite integral from a to b. The delta x becomes the dx, but what happens to this square root? Well, the square root, the 1, the plus, and the square don't do anything, but what happens to this delta y over delta x? Well, if you go way back to when you first defined derivatives, one definition of the derivative was the limit as delta x approaches 0 of delta y over delta x. In other words, this ratio of deltas becomes the derivative of the function. Square root 1 plus the square of the derivative of the function. And that is the integral that will calculate arc length. To calculate arc length of a continuous function from a to b, it's the integral from a to b of the square root of 1 plus the square of the derivative dx. Everything else we do in this section is based on this integral. So let's take a look at some examples.